Okay, YouTube, my last couple of videos we've been graphing rational functions, and what I really want to do is focus on an example of a rational function in which we have no horizontal asymptote. And so we did kind of indicate this in the second video that basically if the degree of the top is bigger than the degree of the bottom, or in other words, if it's top heavy, we basically said that it has no horizontal asymptote. But I actually have more to share than that in this video. So we're going to say this. We say if the degree of n of x, or the top degree, is just exactly one more than the degree of d of x, what we get is what we refer to as a slant asymptote. Okay, this is some linear asymptote that our graph is going to get really, really close to, at least its y value is going to get close to, as x goes way to the right or way to the left instead of a horizontal asymptote. So looking at this rational function here, what I want to work on is finding this horizontal asymptote. And so let's go ahead and run through actually what we know how to do up until now, which is simplify this if possible. I notice that the top has a GCF, and on the bottom we get x plus 1. So nothing simplifies here. In terms of getting this graph though, let's go ahead and start by finding the x and y intercepts. So to find the y-intercept, you just plug in 0 for x, and you can see that even from the original expression, we're going to get 0 over positive 1, which is 0. So we have a y-intercept at 0. This is also going to guarantee that we have an x-intercept at 0, but the x-intercept, we would set the y equal to 0 and solve this. And that's only ever true if the top expression, or the numerator, is equal to 0. So setting x times x minus 1 equal to 0, we can see that we're going to get two solutions to that, x equals 0 and x equals positive 1. So we also have an x-intercept at positive 1. So we've got that as part of our graph. So now that we've found the x and y intercepts, let's go ahead and talk about vertical asymptote. Recall that a vertical asymptote, VA, is going to occur for any x values at which the denominator is equal to 0. And I can clearly see that negative 1 is going to be a value at which we'll have an undefined spot. So I'm going to go put that on my graph. Okay. So now we've made it to this point where we ask about the horizontal asymptote. And what I can tell you is, if the degree is top heavy, it has no horizontal asymptote. And I certainly notice that I have a second degree divided by a lesser first degree in this particular case. So since that's the case, I'm going to give you a piece of advice. If you have a slant asymptote, then n of x is exactly one more in degree than d of x, exactly 1. So what I can tell you is we can actually find the slant asymptote. We're going to write here none for horizontal asymptote for right now, but the slant asymptote. The way we find this is you do long division of the synthetic division of the top with the bottom. So I notice that the top here is x squared minus x. If I'm going to synthetically divide this here, I would say I have a 1x squared, negative 1x, and 0 constants. And since I'm dividing by x plus 1 as a factor, then the 0 potentially is negative 1 that I'm putting out here. But what I basically want to point out is the quotient of the division. Okay? That is the function of the slant or oblique asymptote. So when we do this here, we drop down our 1, we say negative 1 times a positive 1. That's a negative 1, plus a negative 1 is a negative 2, times a negative 1 is a positive 2, and we get a 2. This is our remainder right here. But what I want to point out is this is our quotient. And that quotient right there is always the equation of the slant asymptote. So I would say y equals 1x minus 2. This right here is what we're going to write over here for our slant asymptote. So again, if you have top heavy in degree, just by 1 degree more on the top than the bottom, then what we'll do is either synthetically or long divide, and that quotient will always be the equation of the slant asymptote. I'm going to put this into a different color because I know that I don't want to confuse this for points on the graph, but this, if I were to graph it, I would go down 2 on the y-axis, that's our intercept, and it has a slope of 1. So we have this line here that is going to go like this, and I'm just trying to make this really well. Sorry to make it look like a solid line. But this, as a matter of fact, is the line y equals x minus 2, and this is our slant asymptote. All this means is that as our graph's x values get very large to the left or to the right, our graph is going to follow along this green line instead of follow along some horizontal line. So just as we've done in previous videos, what we want to do is we want to table out some values, always. And we say, well, what values should we table out? It's always the rule of thumb that we'll pick 2 to the left of and 2 to the right of every vertical asymptote, which I failed to label on this one. So it looks like we need negative 3 and negative 2. And it looks like we don't need to worry about 0 and 1 because they've already been found. So when we plug in negative 3, I'm talking about maybe the factored expression up here. We get negative 3 times negative 3 minus 1 all over negative 3 plus 1. And so in this case, we get negative 3 times a negative 4 is a positive 12. All over now, negative 3 plus a positive 1 is a negative 2. So we get negative 6. And then going back and doing this again, except for a value of negative 2. We'll plug in a negative 2 here, a negative 2 here, and a negative 2 here. We get negative 2 times negative 2 minus 1, which is negative 3. So negative 2 times a negative 3 is a 6 over negative 2 plus a positive 1 is a negative 1. So we would get a negative 6. So it's interesting that this happens, but we would say, okay, going left here, looks like I would go left 2, down 6. 1, 2, 3, 4, 5, 6. We have a point on our graph right here. And then left 3 down 6 is just going to be right here. So how can our graph look like this? Well, I know that as far as what it does out on the ends, it gets really close to this horizontal or slant asymptote. So also noticing that it's underneath it right here, I would say that our graph actually just creeps up and goes through these 2 points and then curls back down and must decrease without bound as we get close to that vertical asymptote. Likewise over here, really close to this x value, our graph must have been increasing without bound, going through here, and then as we get really big x values plugged into this, we notice that our graph is just going to keep approaching this slant asymptote right here. So this would be the graph of our rational function. So remember, if you're looking for a slant asymptote, it is the quotient you get when you divide the top by the bottom. That'll be the equation, the slant asymptote. Cheers.